Welcome to Calc Chats 34. Today is our first video involving differential equations, and so we're going to dive in by learning about initial value problems as well as slope fields. So our first big question is, what is a differential equation? So a differential equation is any equation involving a derivative. Looking at the equation y equals x squared, that's not a differential equation. But if I took the derivative to get dy dx equals 2x, this is what we call a differential equation. Because I have the derivative, and I have on the other side of the equal sign something else. So we've been dealing with differential equations, but now we're going to start looking at differential equations often involving x and y, as well as kind of how to model different phenomena using the differential equation. So first we have to talk about general versus particular solutions. So if I was looking at the differential equation, dy dx equals 2x. If I wanted to try to integrate this to try to get back to the original, I can't. So what I would want to do is I would want to get this dx somewhere over on the other side with my x variables. I want all my x's together and all my y's together. So I could just multiply both sides by dx to get dy equals 2x dx. And the reason I need this is because when I integrate, remember I need that dx. I can't just take the integral of 2x, I have to take the integral of 2x dx. So when I integrate both sides, when I integrate 1 times dy, so 1 with respect to y, I'm left with 1. And when I integrate 2x dx, I'm left with x squared. And then because I'm integrating, I have that plus c. So this is what we would call a general solution. So this has no c value. We don't really know where it is located on the graph, except that there's an x squared. But again, the c kind of determines the location of our x squared, whether it's up or down. So this is our general solution. If I wanted to find a particular solution, let's say when x equals 0, y equals 5. So if I was given this information, then I could find a particular solution. So what I would do is once I found my original equation, I can plug in 0 for x and 5 for y. So 5 equals 0 squared plus c. And so I end up getting c equals 5. So my particular solution for this bit of information would be y equals x squared plus 5. So again, this is my particular solution. It gives me a little bit more information about the graph. Now, these types of problems are generally called initial value problems. So again, we'll be asked kind of the same question to find the particular solution. If we're asked to find the general solution, we just have to find the integral and we'd be done. But we're asked to find the particular solution to dy dx equals e to the x minus 6x squared, whose graph passes through the point 1, 0. And so I need this information in order to kind of figure out what that particular solution is. So I'm going to rewrite dy dx equals e to the x minus 6x squared. Again, multiply both sides by dx so that I can integrate. So dy equals e to the x minus 6x squared times dx, and now I can integrate. So y equals, the integral of e to the x is e to the x minus 6x cubed divided by 3 plus c, and so this equation just ends up being e to the x minus 2x cubed plus c. And so it gave me the graph passes through the point 1, 0. So 1 is my x, 0 is my y. I'm going to plug in 0 equals e to the 1 minus 2 plus c. And so when I solve for c, I get c equals, subtract e and add 2 to both sides. c equals 2 minus e. So my particular solution to this differential equation is y equals e to the x minus 2x cubed plus 2 minus e. Here we go. So here is a DIY for you guys to try. So it asks to find the particular solution to the differential equation ds dt equals t times 3t minus 2 and s equals 0 when t equals 1. So my suggestion to you is to distribute that t before you start to integrate. So go ahead, pause the video, and try this yourself. So here below, we separated our variables first, and then we integrated, and you should get s equals t cubed minus t squared, and our c is 0, so there's no adding. Our next topic goes along with differential equations. We're using differential equations to find slope fields. So slope fields is basically just a graph, and we put the slopes of functions on the graph, and it kind of looks like this weird mess below. So it's a bunch of tick marks that represent the slope. So if I was looking at this slope field right below, if I looked at the point 0, 1, my tick mark is horizontal. That means that at 0, or sorry, that's not 0, 1. That's more like 0, 0.25. At 0.25, the slope is 0. Looking over, let's say, 0.75, 0.25, that slope would be about 1. And so this is just basically what a slope field is. We can read the certain points and find the particular slopes. And this entire thing represents the general solutions of a differential equation. If I wanted to find a particular solution, all I would really need to do is to kind of follow the path of these tick marks. And so if I notice, I kind of start off steep. I'm going to erase these two. Start off steep, and then I kind of even out, and then I come back up. So we kind of, it almost looks like a cubic function here. And so this would be an example of a particular solution. So we just follow all of the tick marks along one path, and that's a particular solution for our differential equation. So in this example, we're asked to construct a slope field given the following differential equations: dy dx equals cosine of x. So what we first want to do is we want to set up a table, and this is how I would recommend setting up a table if you're asked to construct any slope field. So we have our x, we have our y, and then we have our dy dx. And looking at this equation, I know we don't have a y, but it's just kind of good to get in the habit of, for when you do have, we could have, let's say, cosine of x plus y. So it's just a good idea to get into that habit. And then I'm going to have right beside it just kind of a basic coordinate plane. And I'm going to, since we're in terms of cosine, I'm going to mark pi over 4, pi over 2, negative pi over 4, pi over 2. So I'm going to go back, and what I'm first going to do is I'm going to plug in x equals 0, pi over 4, pi over 2, negative pi over 4, negative pi over 2. And I'm going to look at y equals, let's say, 0 for all of these first. So for y equals 0, when I plug in 0, so cosine of 0, that should get me 1. So dy dx equals 1. So then I'm going to go over onto my graph, and at x equals 0, y equals 0, I'm going to mark a slope of 1. Let me mark this in a different color. So this is about a slope of 1. Again, I'm not perfect artist, but this will kind of do. So then looking at pi over 4, we should get root 2 over 2. And this is about 1/2. I'm just kind of going to guesstimate it for that, for our sake. And at y equals 0, it's about 1/2. So my slope is kind of a little, let me redraw this, a little less steep. So pi over 4, a little less steep. So it's kind of like this. And then by the time I get to pi over 2, if I plug in pi over 2 for x, I should get 0. So my slope is 0. And if I notice for all of these as well, no matter what I plug in for my y, I will get the same slopes for dy dx. So I'm just going to go ahead and for y equals, let's say, 1 and 2, I'm going to draw the same slopes because my equation is not dependent on y. So now for negative pi over 4, when I plug in negative pi over 4, I should, again, still get a positive root 2 over 2. I'm approximating to about 1/2. And then for negative pi over 2, that gets me 0. So going to my graph, pi over 2, we said was positive 1/2. So it's a little less steep. And then pi over 2 was 0, negative pi over 2. So I'm just going to also go a little bit below. And if we kind of went further, if we zoomed out a little bit, we're going to see kind of our cosine curve start to form. So this is really, really bad. But we kind of get the idea of our cosine curve. So this would be a perfectly good slope field. You don't have to draw the blue part, I just did, but this would be a perfectly good slope field for y equals cosine x. So here's a little bit of a harder DIY problem. So this, instead of asking you to construct the slope field, it's asking you to find the equation that matches. So my suggestion is make just a small table of values to try to kind of look at the slopes and to what they match with this particular slope field. If you want to kind of skip this DIY problem for now, it's perfectly fine. We're going to come back to it in class for these types of problems. So go ahead, if you want to try it, pause the video, see if you can figure it out. So the answer to this is C. If you notice along the diagonal y equals negative x, those slopes are all 0. So this kind of tells us, let's say if x equals 2 and y equals negative 2, that slope is 0. So that's kind of a big key indicator as to how we could figure this out. So here are the following ABC problems for this video. So A is asking you to find the general solution to the differential equation 5x to the 4th minus secant squared x. The second one is asking you to find a particular solution to the equation 3 sine x and y equals 2 when x equals 0. And in this third exercise, you're trying to match the different graphs to the specific differential equations. So go ahead, try these problems. Just kind of note what you can get through, what you can't get through, and please make sure you write down what problem you were able to get to, so that way when you come to class, you're able to sit with that particular group and get the help you need. So go ahead, pause the video, try out these 3 problems, and see what you can get. So number 1, you should get y equals x to the 5th minus tangent x plus c. Not number B. Letter B, you should get y equals negative 3 cosine x plus 5. And for 20, I guess, C, A is graph 27, B is graph 25, C is graph 26, and D is graph 28. So please come to class with any questions that you may have, and please make sure to like and subscribe. Thank you for watching.